Okay, now I switched on the recording. Uh, um, so from the very beginning, and today we will talk about homework and our projects, and we will talk about the hoteling game as the basic for our research and for our investigation and for our project. Hoteling is a very well-known mathematician there, and we are interested in his hoteling game. So we have an interval from like 0 to 1, and we have two sellers here, one and the second one. So the position of the seller is the point, like 0.1, 0.7. So there is just points. It's not two-dimensional, it's just one-dimensional. And there are a lot of customers. In this game, we think, well, we consider the situation when we have universally distributed customers along this beach. So we have here several customers here and so on. So the density is the same all along this beach. And the game that these sellers have to find the place for their market or shop, ice cream spot here. And the idea is that customers, they will go to that seller who is closer to them. So here we can see that customers from the left, they goes to the A seller. So this is the territory of A, and the next one, the right part of the beach, these customers will go to the B seller. So it's very intuitive. So there is no great problem with understanding or considering. In the real life application, of course, we cannot consider that it is a universal distribution, and sellers, maybe more sellers, but it's very good model, because usually, as we can see on photos on beach, so distribution is very close to be universal. Well, and but maybe it's not an equilibrium. So we can consider another situation when we have two sellers, but one seller, A, he's a bit more, he moved to the right here, and now he had more customers. So he had customers here, and he had more profit. So it's better for A goes as close to B as he wants. So here, okay. And for example, equilibrium is a symmetric one. There are different investigations, and there is a special very good quality article about equilibriums of such situation, and it's not very easy one when we consider very sophisticated type of equilibrium. But in this very simple thing, we can find a Nash equilibrium, and usually one of equilibrium is symmetric one. Probably, yeah. But the idea is not to investigate this game exactly, but we want to find solution for more interesting case for logistics, because it's okay, but it's very simple logistics. And what we want to do, well, what I suggest to do, so we can take a graph. Well, before graph, I will give you an explanation. There is a special game. Well, it's not a usually game, it's optimization task. So let's imagine that we have a graph. And we have customers. So it's just roads here. And we have customers here. So we can have universal capacity, or we can have numbers. So 10 customers here, 5 customers here, 20 customers here, 1 customer here, and so on. And we are looking to good places for our for our shops. So and the problem is to find one of the variants of this problem is to find best places that are close enough to these customers. In Moscow, it is called like walking accessibility. So it's the play. So we think that, well, no, he's happy. Okay, that no more than 20 minutes. No, oh, okay, sorry. We'll make him funny. Okay, and there is a shop, and we want to create such shops such that every customer can have access to this in 10 minutes or less. It's very similar to this idea. But here we can say that we have some utility function, so our profit. And we say that our profit, so it's like a salary, it's a number of customers who are close to our shop here, and minus number of our shops here. And we can say that our shops should be not too far to those customers. For example, it could be only one age, but I would like to set another problem when we don't have a restriction on ages. So let's imagine that we have several sellers. So for example, and each of them, well, we can start from the very beginning, from the very simple case. So the first one have to choose the place for his shop, and the second one, for example, this one red, and this one blue. So they have to find spots for their shops, such yeah, and customers. Well, we have distances here. For example, 5 kilometers or minutes to go, and a customer from the spot, he tends to go to the shop which is close to his spot, to his place. So for example, is here 5 minutes, here's 2 minutes, and 4 minutes, and then all these 5 customers will go to B. But this guy, for example, 7, and here 3 and 2. All these 7 customers will go to R. There. Okay, so it's some kind of game here, and each of these producers or sellers, they have to choose the place for this for his shop, and we want to consider several variants. Well, there are modifications. So the first modification is a normal form game. I will tell a bit more about these games later. So in general, they have to, briefly, the description of normal form game, that they have to choose independently and simultaneously these places for their shops. What they should do if they want to place their shops in the same place. For example, if we have such graph, it's obvious that the best solution might be to place in the center. So what they should do? There are several variants. One variant is just that they have to split their customers. For example, if here is this place was chosen by red, and at the same time by blue, and we have 10 customers here, and for example 0 there, these empty places, then 5 goes to red and 5 goes to blue. It's the most intuitive way of dividing customers among these sellers. So the first variant is that they have to choose. It is very important to say that usually we think about normal form games as the game when they do simultaneously and so on. But this game not only for cannot be applied. Can be applied not only for this situation, but also for another situation. And I will tell several words about this. So let's imagine that we have several agents and they have utility functions. Well, utility functions. How should we find the equilibrium of Nash? I have described in the previous lectures the details of this, so I'm not sure that I should recall, but maybe I should. So the basic idea of the game that we have a number of set of agents, we have a set of strategies. Here we have set of strategies, a set of places where they can place shops. And they have special utility functions, U or F, that describe their profit, their utility, when everyone has chosen their strategies. Okay. So you. So for the first agent, for the first player, we have a special condition here. So it's the utility, and there is a special term that is called best response. It means that this function should show the best choice, the best strategy for agent I, if we are given all sets except this specific strategy of this agent. So if every agent, another agent, he has chosen his strategy, then what is optimal for agent I to choose? And the answer is the best response function. So it gives it takes strategies and gives the result. Sometimes best response is not only one number, but a set of numbers. Here we can consider, well, I think we can start from the variant where best response is a function. So we have the result is not a set, but a number, for example, from real numbers, a number from real numbers. Okay, best responses. And the Nash equilibrium so means that if you it's a way of calculating the Nash equilibrium here. So if we have best response, the system of best response, then the solution of this, all solutions of this system are Nash equilibriums. This is the property. It's very useful because it gives us a very direct way, because algebraic the system of algebraic equations are very common in mathematics, and there are a lot of methods how to solve them. If it is linear, like we have in a Carnot competition or in some other games, so we have a system of linear equations, so it's very easy to solve this one by special methods. But how can we get this? And there is a special part. Some Nash equilibrium can be found as a limit of a transformation. So we can say that we can put indexes here. So it's strategies here for best response, and here we have strategies with previous index. It looks like if you have a vector of strategies, then we transform it to another vector that is a best response from the inputs of the previous ones, and so on. Well, it is known that if we have sometimes we cannot get the equilibrium using this method because we have to find the right vector. Sometimes to find the equilibrium, we have to guess correctly the equilibrium itself. So, but in some cases, if we for two-dimensional case draw a diagram, so we have some kind of dynamic, and in some cases there is a point stable, and in general, so the solution is just the stable point here. So it's a point that after transformation will come to the same point, to the point itself. If we were talking about groups in mathematical theory, it could be identity transformation for this specific point. Okay. And in this case, it means that we can consider dynamics. So if we have several players, several agents, several sellers, and they do not have to choose their actions, their strategies simultaneously. No, they can choose, for example, every day, one day, the second day, and so on, until they go to the equilibrium. So they come to the situation when they don't want to change anything. And this is the equilibrium, the Nash equilibrium. If we had, for example, the situation with ice cream and beach, so we have here the position of the seller, so from 0 to 1, and we have several steps. So we might imagine that they have some position initial at the first day. He was observing the position, the previous position of his opponent, and choose the best response for this position. But this guy, he also choose the best position for the previous, and so on. And we can draw a diagram. For the specific case, a hotel game, of course, we will have not such diagram, but another one is just an example. For another game, we can have such graphs. So the Nash equilibrium is a stable point for the such transformation of best responses, because it's not a very common situation when people have to choose simultaneously. But sometimes they have to. For example, we can imagine that they have to go to the beach and find the place there. Okay, it's the very beginning. So it's not even our task. It's not even our homework, but it's the basic of this. So we will need all this knowledge to create to solve the homework problem. Okay. Okay. So we have here a game, and we have some utility function, and we have here some customers. Yeah, but here we have graph, and the first version is a normal form game. Another thing is extensive form game, and the extensive form game means that they, for example, they have another ring here. So, for example, we have like a monopolist, so the man who has a lot of money or power, and he wants to find the place first. So he comes. Oh, he just came early in the morning. So it's the same for this game. And then the second guy, for example, blue one, he comes and he has to choose the place, but he already knows the place that have been chosen by another player. This one. Wait a minute. Sorry. Okay, we can continue. So sorry for this disturbance. Okay, and now we can consider this game here. So in extensive form. So we can imagine that the first one has a right to find and or to choose a place first, and then the second one, and so on. And we can imagine some kind of competition competition between these agents for ordering. So they can pay money to go before the second one, to go to be the first one who has to choose. But it's another game, and maybe we will consider this modification later. So we have a normal form game, extensive form game, another thing, multi-agent, when we have several agents. So it's not a game of two, but it's a game of several players. And we also can consider situation when a player have players, they have to choose not only one place, but they have an opportunity to choose the places for several shops. And in one situation, they have a certain a number of shops. For example, the player red, he has 5 ice cream sellers, like employers, and blue player, he has 7 such sellers, and they have to place them. And the strategy now is not one number, but it's a vector of 5 numbers. Okay, so it's multi spots, multi shops, and we can consider multi agents with multi shop. But in some cases, it's variant 5. We can consider situation when we have not we don't have a fixed number of shops, and they have just like here some costs for these shops. So they can have any number of shops. For example, they can place shop at every point, but there is a cost, and maybe it's not a very good idea to place shops too many shops here. It depends on customers and so on. So it's not limiting. So it's no restriction, no restriction for the number of shops here. Okay, 5. And it's here, and we can mix and combine several variants, modifications. And I think that we can have these modifications for our project with this course, and we have consider them as a homework as well, some of them. Okay. So the idea here that we have a graph here. We fix a number of players. We fix a set of possible strategies and utility functions. It's like a game. So there is some kind of an ambiguity. So I use G for graphs and G for game. This one is a graph. graph, and we have here game. Here, so it's a game, it's a graph. So it's some kind of game on graphs. There are special topics and direction of investigations considering games on graphs. And Jackson, for example, he used several ideas. But usually people, when they talk about games on graphs, they think that the opportunity, that strategies are edges. So agents can make edge or create roads there, or friendships if we are talking about social networks. But here we have a special kind of games on graphs, so we have to find. And then there is an equilibrium. And homework is to create in Python. If you're not familiar, I will give you a very short introduction to Python. Or mathematical, maybe theorems. But it's better to create a software here that can get a graph and get a game and provides us with equilibrium, Nash equilibrium. It's not the complete story, so we have to add here the uncertainty and logic and so on. But we will use it when we will talk about different types of equilibrium, and we will use special or special issue with knowledge. I will tell about it later, so a bit late. So we have here task, so we have graph, we have game, and we have to find we have to create software to find an equilibrium, or equilibriums if you have several. But for homework, we can find only one. So one and maybe others, but at least one if this equilibrium exists. Okay, what about knowledge? Why I have mentioned it, but in some cases, it could be the case that several roads are not known for all agents. For example, this road is known only for red, not for blue. It means that if a blue player has to find the place, he cannot consider this place as the best one because he doesn't know that these 5 customers will go to him, because he doesn't know that this road exists or work properly. So maybe he think that these customers will choose between this road, so it's 6, 2 plus 4, and this one, 7 plus 12. Oh, 5. And he will never place here his shop. But at the same time, our red player, he may be not aware of this road. This one is known only for blue. And we have to find the solution. Of course, if we are talking about normal form game, we can find an equilibrium, but it's not so funny. It's not so interesting to investigate the properties of such a game. But if you have extensive form game, it will make sense to have special method, and I will tell a bit today about this method. It has connection with the database and a very important muddy children problem. I have described it, but I will recall because it's a very interesting thing. So the setting, this one. So we need to place here. Sometimes people, they use fourth a member, like information or knowledge or beliefs is just a special term or special information about knowledge here. We will talk about this, but the basic idea that here we have a coloring of this graph, so some kind of coloring. For example, we can say that age can be white if there is no player, or just maybe not white, but any other color. It can be red if it is known only by red. Hello, by a red player. It can be, for example, blue if it is known only by a blue player, and then violet or black, for example, if it is known for red and blue players, and so on. So it's a coloring, but we can replace coloring by just numbers. It's okay. So this information structure is just some kind of coloring on these graphs. How it looks like. For example, we have here one city or one block of customers in our city, 10 customers, 20 customers, 30 customers, and maybe 10 customers. Several blocks. So we have rows here. Yeah, and I will use coloring right now. So we have two players. Two players. And we have, wait a minute, like red one. So this road is known only by red player. We have blue. These rows are known only by blue players. And for example, violet, maybe this one. These rows are known for blue and red players. It is not very interesting to consider roads that are not known by any player. So, and we have this city. It's a graph. It can be a directed graph, maybe not. And we have a game here. We have discussed game, so it's special plus game. And then we have to find an equilibrium for these players. For example, the output might be, let it be alpha, beta, gamma, delta, epsilon. The output is just red. It has to choose, and the best idea is to choose alpha, then blue, he choose delta, then red, choose gamma, and beta skip. And B and red, they just skip. They don't want to place more shops. And we have here, so here, there is red shop, there is red shop, and there is blue shop. And this is the solution of the game. So I think that this is the good idea to combine every conditions, every ideas of our course in one game, in one product, in one project. So we have here logic. We use logic in equilibriums, but also we can use there in coloring here. We use game theory. It's obvious because it's a game. We use logistics here because we use roads and algorithm. There are special algorithm, and we use some kind of optimization. There is a very interesting thing that I would like to add if we will be successful with this game. We can consider a situation when after they have divided the territory, between this. Sellers, by the way, we can see that customers from this spot will go to red. From this spot they go to red. From this spot they go to blue, and from all these they will go to blue, because this shop is the closest to them. So the utility for red is not so great. So the blue player here has his advantage, but we can check if it's an equilibrium. An equilibrium will occur if red player he doesn't want to change. So he doesn't want to change his shop, for example, to this place. Here it's not the case. Red player he might want to change the location of his shop, so it's not an equilibrium. But if such situation will occur, then we will have an equilibrium. Okay. It's for a normal form game. For extensive form game, there is no such choice there. Well, there is a special situation with Nash equilibrium. I will tell a bit later. Yeah, and after this territory is divided, we can solve here the problem of a traveling salesman using branch and bounce algorithm. The idea here that, okay, they have divided customers between these sellers, but what are costs for this seller to sell their products? And one of the solution can be the following. So let we have some area for red player, we have some area for blue player, for example, in this case, or maybe we have another area for red, if red player has several shops. And then we want to set the problem that red, his costs is not only depend on the number of shops. It's okay, but we can allow only one shop or maybe two shops. But costs depend on the cycle here. So the solution of the traveling salesman person. So how much time this seller, red seller, will use to work with customers, to achieve all customers. And maybe it's a good question, and we can try to find the idea. So customers, they are assigned to this seller, but seller has a problem of delivery, and he has to solve his traveling salesman problem. And now we have costs in this function, as I have described before here. So utility is not just number of customers and number of shops, but also minus a way or length of the solution of delivery of traveling salesman problem there. Okay. Or we can consider the spanning a tree here, and so on. So there are many ways of how we can model the service of the seller to these customers. But we can start from the beginning. So when we just look at this game, but it's not. It's only a part of the our problem, our project, our homework. I think that it will be a good idea not only use all these, but we also will use Python, of course, to create this software, and also we will use real data. What kind of real data? There is a special site. You can use another one, but I prefer this one. I can recommend it. I use it in my another course. So it's Colorado University in the United States, and they have very large database of different graphs. You can check fictional, neural, disease, animals, sports, and so on. I have found roads. For our purpose, so logistics is about roads, but not necessary. We have a network of airports, for example. Sorry, not language. Airports and so on. Travel here. I have used it, just roads, and I have several graphs. So it's United States graphs. It's Barcelona, it's Hessen, Chicago, Rome, Philadelphia, Birmingham. It's maybe Great Britain, Chicago, and so on. German highway. We can find this network because this one, Bryce paradox network, is very small one. I have described this paradox before, so it's a very small network. But we can check, for example, Chicago. Okay, Chicago. There are a lot of roads here. So we will need a very effective solution for our problem. Because we can simplify if we have a restriction on places for our shops. So we can say that we do not allow our sellers to place shop everywhere. For example, we are on the market and we have only a real estate market, and we have only 3 or 5 places for shops, and they have to choose between these places. And even if we have a very large graph, we have only 3 or 5 alternative places for shops, and it make our problem much simpler. Okay, so and in this case, we can, but of course, we have to imagine the situation, the informational structure, because we don't know this informational structure. We have to imagine how many players will play this game. We don't know, and so on. Of course, if we have several data, but more data about, for example, locations of Amazon, or maybe, I don't know, Apple stores and other shops, if you have such data, you can place it on this map and check the best places for the specific, for new seller, if he wants to be closer to the customers that have to choose between this new customer, this new seller, and sellers from already existing large networks. So it will be some kind of real problem. So if you have business, or your friends have business, so it's a real problem. Where should you place your shop? Because you have to find a location, and logistics is very important there. Of course, there are a lot of details that we don't consider here. We don't consider traffic and so on. But you can add these details to your model if you want. Okay, and if we download, so we can download age list and so on to our problem. We can get like sorry, not here. It's an example of such program. It's also the solution of the game. Solution of the game. It's just some part of my another course about social networks, and we can have such graph which we have downloaded from this or another source. So we have a graph of city, and we want and we assign then customers. We assign length of the rows, and we fix players. I think that we can start from 2 players, for example, and one shop for every player. And we can find where they should place their shops so that it will be equilibrium. And yeah, it's social networks, but you can imagine the same for the road networks here. It can be very sophisticated graphs. I have explained how we can apply our algorithm to these graphs, even if these graphs are very large. So we can just restrict the places for our shops. Okay. Yeah, here. And that's all. So but here we can not only find the software, it's okay, but we also we would like to find the properties of these settings. So what if we have more players? What if we have more shops? What if we have different graphs or informational structure? And I think that it will be a good idea for our project, because we have some kind of scoring for our projects for in our course. So it can be a good idea that we can, well, you can create a presentation with the results of such analysis of a network. For example, Chicago networks, you have restricted uh, and you have found several locations, and you created a game, and you check how many players, about equilibriums, informational structure, and so on. And it will be diagrams and very good science. I mean, it's very experimental, of course. Well, because there will be no theorems. But if you consider a graph not a specific one, but a type of graphs, like um, random graph, or then it could be a theorem. But and in this case, it will be a real theorem that is very difficult, maybe to prove. Very sophisticated theorem that can be published in high quality journals. But if we consider not the specific graph, but a class of graphs, for example. Or maybe if you consider specific very important graph, but maybe not so such a high quality journal, because it depends. It depends. Okay. So we have here. Yeah. Unfortunately, I don't know if you know Python or not. Maybe you don't like. Uh, you can use another language like Haskell, maybe, if you like R. But I recommend using Python, because usually I use Python in my work, and there are many libraries there. You can check if your algorithm is uh, very efficient in comparison with a machine learning algorithm. You just include the machine learning library, like old TensorFlow and new ones, and check if your solution is better in some cases than these tools can provide, and so on. So you can create some kind of more interesting investigation. But it's not obligatory to use this language, though I recommend to you, if you don't like Python or don't use this, I will give you a short introduction to this language. It's, for our purpose, this introduction will be very short, so because we don't need all properties of this, all power of this Python, because we don't need maybe lambda functions, or maybe recursive expressions, and some compiler optimization, and so on. So we will need just some kind of software that works, and it's okay, more or less effective. Okay. Okay. Nice. Do you have any questions right now? If you have, let me know. I will try to explain. Okay. Of course, I do not. Yeah.
Sorry, what is the deadline for the task?
Yeah. It's very important. I understand that this task is rather complicated, and maybe if you are familiar with logic and game and optimization, maybe it's just work for you for one evening. So you just sit down and write down everything, because you did it before many times, and it's fine. But if you didn't, it can be very complicated task, and maybe it will be very a difficult one. So I think that I will need the complete this one by the end of the fourth model, because we have third one and fourth one, so we will need by the end the final edition. But preliminary editions, I think it will be good if we have at least maybe not the complete solution, but some code that do something, or some explanation, or some kind of progress by the end of the third model. So a preliminary one by the end of the third, and the last one, the final one, before the exam. So it will be some kind. You will have a presentation there about these results, and you will have this homework already done, and there will be exam about some maybe theoretical theorems that we have been discussing for several lectures about traveling salesman person problem and branching bounds algorithm and so on. And that's also and it will be scoring. So what kind of preliminary result you should get by the end of the third model, I will maybe specify on the next lecture. But now I recommend. So it's not a homework for just 1 week. It's very important. So it's a homework for several weeks, maybe 2, 3, and so on. Maybe for 1 month or several months. So it's very long. But I recommend using agile methodology. So as we are on the computer science department, so we can use a different project, different types of project management. And I recommend agile. I like it very much, not waterfall, but agile. I will tell just the main idea of this, not in full details. Usually agile means that you create some kind of working example, and then you increase its complexity. So, for example, you have a solution for three for a certain graph with three nodes or 4 nodes for 2 games and for very specific information, and it works. And then you create complexity, you increase complexity, and you can get the better and better result. I think that we will have to have some results by the end of the third, but the final thing by the end of the fourth model. So this is about a deadline, but I recommend to start from the very beginning, maybe next week or maybe even this week, to read carefully some ideas. If you don't know Python and other theory of this, maybe you will need to read it and investigate, and you definitely will have several other courses. So you will have to plan your activity during this. So I think that you should start maybe next week. So this is about deadlines. And of course, I'm open to explain details of these personally, or maybe during the lecture, and tell some details. Right now, before our break, I would like to tell maybe about muddy children problem or extensive game problem. Yeah. Okay. By this by this point, have I answered all questions, or should I answer more? Do you have any question? Okay, I think that
about the assignment.
Okay.
How many assignments will you be giving us?
Okay, I think it can be a single one.
All right. Have you already given us the homework, or you're waiting for another class?
Okay, I have described the homework right now. I will send you the formal description of this. And this will be the start of our homework process. And then you will have several weeks or months to do your homework.
Okay.
Okay. Yeah, the homework consists of several difficult things. So you should handle graphs, you should handle games, and so on. So maybe your software will have several parts that you will develop during this month. Okay.
Okay.
Nice. Yeah, we have maybe 10 minutes. Okay. So what about database? No, from games. So when we have a normal form game and we have extensive form game, it's extensive. I will start from the normal form game. How can we just find an equilibrium? Okay, the case for two players, or two agents, or two sellers is this one. So we have some kind of matrix. Indeed, we have two matrices with a utility function of the first seller and utility function of the second seller, and their choices here. For example, we have this kind of network. So we have alpha, beta, gamma, delta, and epsilon spots here. And the choice of the of player, just he can place his shop at point alpha or beta or gamma or delta or epsilon, and the same for them. It's for the red or first player, it's for the blue or second. Why do we need two matrices here? Because we want to place the utility function for all combinations for every player. For example, if a red player, he chose gamma, and blue player, he chose beta, then they have a special situation when gamma is red and beta is blue, and we can calculate the utility of those players and replace this number here. For example, it can be just 3 here. So it's there, or 3K. 3K dollars, or rubles, or euros that red player will receive if he chooses gamma and blue will choose beta. But what is the utility for blue player? Blue player, for the same, may have not 3, it's not obligatory. He can have $7, $7K a day, for example. So it's the utility for red, and this is utility. And it doesn't matter that this place is better for beta, for player blue, this one for blue. Because maybe other alternatives is better for blue. For example, here, blue has 10K here, if you choose epsilon. So in this case, it's not an equilibrium, because blue player, he wants to change the place of to change the place of his shop from beta to epsilon, because for the given choice of red player, a blue player will have a large utility. So it looks like this place is very good for blue player, but indeed for blue player, this epsilon is even better. But for red player, maybe for him, this choice is even worse than the choice right now. So it's some kind of game. It's about a normal form game. We can check mixed strategies and other things. We will discuss it later when we will have some kind of preliminary version of our softwares, and we can also add mixed strategies, because it's not so easy. But in this case, we can do this. It's very difficult to find mixed strategies if you have like an original hoteling game situation when the strategy is just the real number. So when the strategy is a real number, then we have infinitely many strategies. And in this case, mixed strategy is not very easy to find. But if you have a fixed number here, a finite number, mixed strategy is just a solution of some linear system. I will show you later how to do this and how your software can do this. Of course, when you when you have to find Nash equilibrium, it's not an easy task, because sometimes it is very hard, like NP hard or something. So, but in some cases it's very easy. So we'll maybe discuss it, and maybe not even Nash equilibrium. I will show you different types of equilibriums, and maybe another one will be more preferable for you. It's normal form. If you have 3 players, we need not matrices, but some kind of tensors, if you like tensors, or just 3D tables, so cubes. The same reason, because we have choice for red player, for blue player, and I don't know for what other color, yellow, for yellow player. And we have 3 dimensions, and we have a cube of a utility cube for every player, 3 cubes. If we have more players, we need more. What if we have strategies for a different, well, maybe we have to play, or we can allow, or we had allowed several shops for the player. Okay, in this case, strategy for every one is not just alpha or beta. For example, if red player is allowed to place 3 shops, then it's very intuitive. Think about it as a vector. For example, he can place 1 shop to alpha, 1 shop to beta, and 1 shop to epsilon. Is the strategy of red for the Tuesday. And for the Saturday, maybe he wants alpha and delta and epsilon. And that's Saturday. And so on. But the main idea that we have several numbers. If you have n spots there, well, we have, let me have n nodes for customers and m nodes for shops. Then we have and players, and they are allowed, for example, k shops. Then all possible strategies for 1 shop is just k shops. So but no, not this. No, it's C. It's a number of combination from M. Okay. Well, I will tell a bit more about combinatorial aspects if you are not familiar with this, because it's not obligatory to know that, but it's just a number, how many variants for us to choose k elements from M, from the set of M elements. So there is a special definition for this. It is defined by factorial. That is just a product from 1 to n. But combinatorial things we will discuss maybe later, if you need it. Here we have to know that just if they have several types of shops. For example, one is just store and one is supermarket, then the ordering matters. So the first one is the place for supermarket, and the second one for small shop. And maybe he wants, in this case, this situation is not the same, because it means that supermarket here in the spot alpha and Here it is spot delta, so it differs if they have several types of shops. But I don't know if we will consider different types of shops. Maybe it's enough to consider just very ordinary shops here. So we have 3 minutes. Yeah, maybe I don't have time for the well, after the break I will show how we can get from extensive game to the normal form game form. What is the extensive form? I will just explain it before the break. It's just like a chess. We can think about it as about a tree. So red player, he had to choose the place for his first shop. So it can be alpha or beta or gamma or other. Then blue player, he has to choose. He can choose beta or delta, but maybe not alpha because red is already chosen. Or maybe he wants alpha too, so he wants to split. And then red, maybe he wants to place his another shop, and then blue, and so on. It's like a chess, so they have to move. Each arrow here is just a transformation of the state of our object. So here we have an object. It's like a graph of the city with shops that are placed at different places. And the transformation is just a put a shop. Or maybe he wants to move. We can allow moving these shops. Maybe it's okay. And extensive form can give us such an opportunity. For example, as I told about a best response idea. So the red player, he choose the place for his shop, like alpha. Then blue player, he choose spot for his shop. And then red player, he can change the place for his shop. Maybe he has chosen alpha, and then he decided after he found that blue has chosen alpha, he wants to choose a new place, gamma. And then blue wants to change, and so on. Maybe it can be cycle. In this case, we have some kind of equilibrium sometimes. But maybe there will be no cycles here if we have iterative number, and so on. So it's the extensive form game. And there is a way, okay, we have time for break, how to get from this representation to these matrices, and I will show you. Now we have a break, and we will be back maybe at, well, not maybe, but at 11:10. Okay, and you will have an opportunity to ask questions, and we will continue with this solution. Okay, 11:10, so we continue. As I have described, the variant of homework is just to find graphs, to find games, and I have to say that maybe some parts, and it is allowed, can be downloaded from internet, so it's okay. So if you found that there is an article or there is a software that can solve this problem, you can just share this, and then your idea is just to understand how it will. Well, not idea. Your job is um, your task is to find them. Um, understand explanation for every step of the software, and then you directly go to the diagrams and checking the um, behavior of this problem, behavior of the equilibrium that depend on the parameters like number of players and so on. I'm not sure that there is such software. Maybe not. Maybe there are general software, but not for the specific case. And maybe there are articles that can explain, and maybe there are theorems about this, but I'm not sure. Maybe not. The problem here is that when we are talking about specific graphs, then it's very difficult to prove theorems, because graphs can be very complicated. The unique, many graphs are unique, and when we have graphs just like graph generators, like random graphs and so on, there are theorems, but maybe not for the specific case. I'm not sure, because it's not very common when you use informational structure, like I have told, and you use game theory and many other things. I think that maybe this setting is new, maybe new in all senses. Well, in most senses. So it's like a scientific problem. But it's okay if you have found, for example, a software. You just say that I have I use this library and I got this result. It's okay, because we are in a 21st century. We know that there are internet outside our room, and we can use it. No problem with this. During exam, you will have we will have several theorems, maybe, or maybe some definition to describe. Then maybe using internet is not a good idea. Maybe it will be not allowed because it's exam. But for your project and for your homework, it's okay. Okay, now I would like to show how we can get from extensive form game to a normal form game. It looks like if we have such a normal form game, well, there is a special type of extensive game, like repetitive, well, that can last infinitely long time. So it's not there is no end of this game. We can make moves infinitely long. So you make move and then again and again and so on. There is no end. And but we can assign a special utility function for this. No problem, like infinite sum or something. This one. And if it has a limit, so no problem. There is for example, in logic, there is a game such that if there is no end of the game, then the winner is the player number 1, for example, or the player for number 2. So if the game is finite with a special property, then the first player win. If there is no end, then the second one, and so on. So it's okay. But how can we transform? Well, what we should do, we can imagine and we can list, for example, for this case, and say, okay, what is the strategy for R, for red? We can say that a strategy is just one of maybe alpha, maybe epsilon, delta, and so on. It's plays, I mark X, I, 0. Okay, the first one. But then he has to choose another one. And we have here, for the first player, the second step, and so on. Maybe infinitely long. No problem with that. It's okay. Because we don't need even countable large. We can have very large set of strategies here, but it's mathematicians. In our examples, it's a finite always, so no problem with this. So we have a finite thing, and since we have, well, accept the situation when they have to, that they can move their shops. In this case, then can move it infinitely a long time, so it's infinitely large vector. It's no problem. We can imagine. We even can program this. We can create a software, and we can create such object. As I have described, we have a Haskell, for example, and in Haskell we can have a infinitely long array or infinitely long array, yeah, or vector. It's no problem. But there are some restriction, and it is possible because of laziness. So you just describe this object, but physically there is no memory for this. I mean, it doesn't need infinitely large part of memory because it's only a description. And when computer needs to get an element, he just calculated an element. But it looks like you use in your program infinitely large set. Okay, it's just a trick. If you are interested in such tricks, I can describe in other lectures some details. But for us, it can be, for example, just finest thing. Okay, and what is it enough? So can we just list all these variants here? And then, for example, if we have here 5, well, how many? Alpha, beta, gamma. We have m variants, and we have a, b, p steps here. Then it looks like what does he have? M in the power of p strategies. So what is his first move? What is his second move, and so on. So for every player, but it's not. For extent, when we have a procedure of transforming the extensive form game into the normal form game, it's not enough to have such number. Yes, we have listed all strategies. It is, and intuitively it looks like it's enough. No, if you know why it is not, you can tell. But the idea of this, that it doesn't, well, this one, but he can choose alpha if only in this point. So if beta choose alpha, then R choose gamma. But if beta choose beta, if blue choose beta, not alpha, then the decision of R is, for example, epsilon. So it does matter what was the information of this, what was the history. And we have to place it somehow here if you want to a complete description of this game. So we have to put this strategy, this function of choice for every node. So though we have here for the choice of B here for alpha red, and for beta also red, in real life, or in equilibrium, only one of these variants is possible, only one. But for the equilibrium, we have to ask R to define our red player to define before the game starts his choice or algorithm for his choice at every such node, such that when the algorithm starts, then we can, using this algo, well, when the game starts, then we can make choices as red do, but without red, because red gave us instructions how to behave in every node. So we don't need red to be involved in this process during the game. We just use his instructions for this. But we need instructions for every node here. For every node, that is red. Red means that it is he who has to choose here. So it looks like we have here, if you have the lines P, also P, yeah, it's not let P is a number of steps of R, the points where he has to choose, but we have to add here number of points where blue player, because if we want to find here all number of nodes, wait, no, not this number. Indeed, what we have is just to find the sum here. So it's just one, it's just M here, choice here. We have at every choice here M variance, and for every variant M we have M square. Yeah, and it looks like we have to sum this members. Okay, but when we do this, so when we have instructions how to choose strategies at each node, then we can construct a game in a normal form. In this case, so the strategy is some kind of history. And if we have a history, so history is just a place of this node, we have to place a strategy like XR. And when we list all this, we can have such metrics. If we have a game of 2 players, so we have history here, and we have history for another player. And in this case, when we have a Nash equilibrium, then we have equilibrium in this game. So there is a transformation, how we can get equivalent normal form game from the extensive form game. Unfortunately, people they don't use, well, not unfortunately. Unfortunately, we cannot use this usually. We can program our software, we can develop it, but we usually cannot do this because it takes very large space for these strategies, because we need to place in the memory or in the algorithm the variance for every these nodes and histories. So okay, and another problem is that we will have here many Nash equilibriums that, and we need to refine them. We need only several of them, and then we can have special types of equilibriums here in this game. For example, there is a perfect subgame equilibrium. That means that let's imagine that we have such an end of this game, and we have the blue player to choose his strategy, and he's the last player who will choose. So there is no other player who will choose. After his move, the game stops. And then we can say, okay, he can solve optimizational problem. No Nash equilibrium, no. We can he can just solve very simple problem. So he has utility function that depend only on his action, and history that is already done, so it's a history. And this is optimization problem. And we can do this for every node. And then we construct some kind of equilibrium maybe. And maybe it's a single one, it could be. But it doesn't mean that there is only single Nash equilibrium there. So there are some details considering Nash equilibrium. Okay, it was a story about a normal form game. Why we need it? Because maybe we want to find the equilibriums here, and yeah, sorry, yeah, here. When we have not a normal form game, but an extensive form game. In this case, we maybe need this table and understanding how extensive form game can be transformed into normal form game. When we talk about mixed strategies, what does it mean, mixed strategies? And Nash, very famous scientist, he proved that there is always a Nash equilibrium, his equilibrium in the mixed strategies. In pure strategies, it's not the fact. What does that mean? So if we have a table or a game, any game, like player one, for example, red and blue, and it could be that there is no such place, no such point that all players are satisfied. So they don't want to change. There are many such games that this blue player, he wants to change here, then red wants to change here, and there is a cycle, for example. So there is no Nash equilibrium, but mixed equilibrium is always exist. What is it, Nash? We can say that red and blue, we can allow them not to choose the single strategy always, but we allow them to assign probabilities for this. So it's some kind of probability distribution here. It's like a coin. They flip a coin and they choose the strategy. And if we allow them to do this, then there is also always a Nash equilibrium there. What is the meaning of Nash equilibrium? Well, in this case, what we have, if we have here probability P1 for first player and P2 for the, well, it's the first alternative, but for the second player, so for the first, for the second, then this thing, the probability of this state is this one. So it should be the case that this this strategy has been chosen in this one at the same time. So then we can multiply these probabilities. So if you have utility here, then our utility is this one. But when we want to find the total utility, then for this strategy, what we do, what we need, we can multiply this probability and sum of our choices here. So it's I for the first, and here indexes of these choices. For example, we can say that it's xj. No, sorry. Like here, and we have x. We have a choice for the first group put, yeah, and for the second player, this one, and we multiply on this probability. So we take a number here, multiply by probability, and add, and so on, and then we have a special utility function for this choice. And then we can find an optimal one and so on. And it looks, we can find such probabilities here that agent don't want to change them. So if we ask him to change, he doesn't want to change them because his utility function, that is indeed this one, and plus for according to these probabilities, all other things here. If you need details, I will provide it. In this case, he doesn't want to change this P1 and so on, because the value here is the maximum that he can achieve by choosing the distribution here. And maybe I will show you later on several examples of this. But it's some kind of special part of this theory, though it is very interesting because we have always a Nash equilibrium, and it's very intuitive and practical one. But we have to make some efforts to understand what is mixed strategy, probability theory, and so on. Okay. Yeah, maybe game theory here is almost done for this lecture, but logic part or uncertainties part, it's some kind of another story. Yeah, a story. Let's imagine that we have a database here. We are at computer department, so it's okay. And we imagine that we have objects that have two indexes, like I and J, for example, I and J. What it could be? Surname, index at surname, and name. Or maybe if he has PhD, or maybe he has no PhD, and his surname or country, or maybe age, or whatever. So, or maybe scoring, or I don't know. We have two numbers, even not numbers. It could be objects, and we can imagine that one player or agent, he can observe only the first one, and the second can observe only the second one. For example, I have been on conferences with my friend, colleague, and we found a lecture there, and I remember that his surname starts with letter F, for example, or B, for example, starts with B. But I don't know who is this lecturer. But I want to download his articles and so on. But I know only the first letter of his surname. But my friend, he knows, for example, his well, the first letter of his name. Oh, he can know his name, but not surname, like John maybe, or Albert, for example. And we want to find the specific person there, and we can aggregate our knowledge to find this person. But if we are in a game setting, maybe we want to know this person, but before my opponent, well, my friend. So I want to find this lecture before he, and he wants to find this lecture before me. So it's some kind of game. So we have some kind of distributed knowledge. So I know only part, and we want to get the whole knowledge, the complete knowledge, but we don't want to share our knowledge to opponents. It looks like it's applicable only for the competitive settings, only for game theory and so on, but not only. For example, if you know there is a robo football, where robots play football, and in France there is a place in Toulon laboratory where they have such robots. They play football, and they have won several tournament, all France tournament and championship maybe 2 or 3 years ago. And the problem is that they don't want, well, the problem, the restriction on these robots is that they have, well, robots, looks like pyramids or something. it was the restriction of this tournament. It's about maybe half a meter, so 50 minutes or something. But they want to restrict the organizers. They want to make these robots autonomous. So they don't want these robots just to share all this information, and then one robot, he can choose the decisions for all robots. They want to have these robots to be autonomous. And the restriction is on the channel here. So it's not faster than, I don't remember, maybe 10 megabits or maybe 100, I don't remember. But there is a restriction. So when one robot has a video input and another one has a video input, they cannot just send this video input to one to another. There is a restriction on this. So they can make some, they can get some information from this and send only part of this information. And it looks like they have a knowledge, but they can't share this knowledge. And there is some kind of special task here. So it's not always about competitive thing, but sometimes it's about cooperative, but under restrictions. In this case, let's imagine that we have a restriction on possible combinations of this. So it's the first element here, and this is the element here, like Excel table. And you have only several parts that are allowed here. Because others just, for example, there was no such a lecture with this first letter at his surname and such, and for example, name Oleg or Dennis, for example. So there was no such lecture at all. But there are several lectures that are allowed to be so, and we have to choose. And then the variant, the process, is that we ask these robots, or ask maybe indirectly or implicitly ask them, and to are they ready to know to make a choice? Do they do you have enough information to make a choice? Because maybe you have already found the specific, and they can reply if they have found or not. For example, if the right version, the right cell, this one, then this guy, he cannot distinguish this place and this one, this man and this man, because there are two variants here for him, and he doesn't have enough information. And for this agent, there is no information, because he has three what are the possibilities, but three possibilities, no variance. But here, for example, if this will be the case, then this agent cannot make decision because it has three opportunities, but this one can, because for this variant, only one possible solution. And if we proceed with this procedure, and we ask them more and more, and they have to reply, then we can just eliminate several variants. If they reply that they don't know the right questions, then we can eliminate this one, because otherwise this agent knows, and we can this one, eliminate this one, and we will stay with this part, 6 variants. And this is the result of some kind of communication in our logical game. How we can use it here? For example, here, if we understand, well, if there is an extensive form game, and we see that, for example, here is just 10 customers, and we know that here is 20, and here is no customers at all, 0, and we are red, and our opponent is blue, and we have like, for example, here. We'd like to place a shop maybe here, because we will have 0 customers, 20 customers here. Or maybe we will place it here because we will have 10 customers here. It's okay. But we can find that blue, he placed shop here. And based on this information, we can say that if it is optimal for blue, then blue knows something that we don't know. What kind of information? If there is a road here, if there is no roads here, it's not optimal for blue player. Why he placed in the block in that block that is not connected to customers? No reason. We think that our opponent is rational. So he's a businessman or seller, just seller, but he has he is intelligent, so he optimized some function. So he is not just the man who flip coin, and that's all. He is so lazy that he don't want to think about it. No. In game theory, we usually think that our opponents are very rational and intelligent. It's some kind of problem sometimes, but for the theoretical purposes, it is allowed to use this assumption. Okay, if there is a road here, only here, then for blue, it's not optimal place here. Well, it's optimal, it's okay, but why shouldn't he place here in 20? Because it looks like a better choice. There is no risks that other player can just beat him, so he can place here. If he has road only here, for example, the same, he has no choice even, well, he has no reason to place it here or maybe here. No, the only reason when he has some kind of reasoning to place it here is that there is road and there is road. So based on our observation, we found new information, and maybe for us it is very important for our choices to know more about this setting. Okay. And another modification of this situation, well, yeah, and right now I will continue with this idea. So we have several possibilities here, and we can list all alternatives. It looks like a possible words. So there is a special term for this in logic and in other theories. So we list all possible variants here. So we have some kind of array of graphs. Based on this information, we create an array of graphs, or we have a graph of graphs. What kind of graphs? To describe this situation, we have one situation when there are roads, and one situation when there is no road here. So two different variants of our city, and maybe our agent cannot distinguish them. And then in logic, it is normal, is that you just connect them and place the name of agent who can distinguish them. For example, red. If this one is blue, and this one is red, it means that a red player, he knows that this road here, but he doesn't know about this road because only blue has this information. So red cannot distinguish them. And we can place other variants of this transportation network, and we will have graph. graph of graphs. It's from a mathematical point is already funny because we have graph of graphs. It's very interesting object, but we can do some interesting things here. For example, we don't know which one is real. So red, he doesn't have enough information to distinguish them. But if blue acts like this is real, or for example, blues say that real this one or this one, blue makes move that eliminate this one as an impossible one. Then red can make his decision. So he realize that only this variant of his graph is real, and so on. There is a special situation. I will show you maybe right now because we have enough time for this. Well, we have some content. So there is a book with a super modular function, branch and bounds algorithm, and so on. And we will continue with this. But maybe right now it's not okay to mix all this content in one lecture. So I will try to focus on this topic, and then we continue maybe next lecture with that book, or maybe this lecture if we have enough time. Let's imagine a very classical one. I will start with this, and this will give you some kind of classical knowledge of this. So formally, it's logic, it's modal logic, and it's even epistemic logic. Epistemic logic. So it's a part of philosophy, or it's part of mathematics. And the game is called Muddy Children Problem. In Russian tradition, we have a special name for this. It's like three wise men. In Russian, it's три мудреца. But usually, this name is totally unknown outside Russian articles. So exactly the same situation, well, mathematically the same situation, is called Muddy Children Problem. So not wise men, but children. And the idea is the same as in this in that setting. So there are three children. 1, 2, and 3. And they have their faces muddy. They played in very dirty environment. Their faces are muddy. Okay. Oh, dirty, but in logic, it's classical to say muddy. Dirty faces. And but they can see only faces of others. So this guy, he cannot see his own face, only faces of others. Okay, and there is a father, or in the setting of wise men, there is a stranger, but there is a father. He told these children that there is at least one muddy children. There is at least one children with muddy face. Okay. It looks like there is no new information for all of them, because every child here, every kid, he can see faces, two muddy faces. So when father he told that there is at least one, every children can say, okay, yeah, I can see two, so at least one, no problem, no new information for me. And then father asked them, but it's important part. Without this part, without this information that looks like very unuseful, so there is just wasted time of telling this information. But without this previous information, this model doesn't work. So there is no solution for this. Okay, and I will show you how it might be. So, and then it's also a very important part. He asked them in terms of epistemic logic, or it's called dynamic epistemic logic, with a public announcement. There is a special term how he can say that how describe the situation when someone he tells something to all others. It is very important that there is a public announcement. It's not just a message to everyone privately. So when we have a public announcement, so I say to all of you, and you have witnesses that all others they listen to me. So it's not the same as I did it privately, because uh, uh, you have common knowledge. So you know not only the message, but you know that others know the message, and you know that others know that you know the message, and you know, and so on. It's infinitely thing. So there is a common knowledge there. So the public announcement is about telling everyone and in public. Okay. And he asked them, do you think, or who of you can say that his face is muddy? It looks like nobody can, because he can. There is no children. Well, there is no kid who can see his own face. They can see only others. So the first one is information looks like unuseful. So there is at least one muddy face, and then the question is, can you? No, we can't. So the answer is no, we can't. No. Then he do it again. He asked them, do you know? Do anybody of you? And the same, no. And it looks like is just infinitely repetition of this. But no, on the third step, every child here, or all children, they say yes. So now, after the third step, they all know that their faces are muddy. It looks like a magic, because why should they know? There is no way how they could know this, but there is a way, and it's a very logical one. And this reasoning was so important that this example now is classical in model logic, so classical that people usually avoid just mentioning it, because it looks like if you mention this example in logic setting, in model logic, it means that you are like a first year student of bachelor degree, and so you're very, very newbie. But it's still classical, and with some modifications, it can be very interesting. And there are several open problems with this. But where is the solution? How can we explain this effect? And there is an idea. We can define that we have, for example, one possible word, and we want to make I don't know, yeah, okay. This is the possible word, world. Yeah? No, a word, if we say about a description, so they're all muddy, and we can say that all faces are clean. Okay, so we know that the real case, the real world, that all faces are muddy. Okay, so this box is a world. And then we can say that there is another world. And first agent, he cannot distinguish these two, because he cannot see his own face. And we can say that for the second, this is true. He cannot distinguish these two. For the third cannot distinguish these two. Okay, and we can move forward. So we can say, okay, but what about the second? So second cannot distinguish these two. If this world be real, then the second cannot distinguish this one and this one. Why? Because it differs only by the face of the second kid, and the second kid cannot distinguish if he is muddy or he is not. Okay, it is and we can get the same world from this one. This agent one, he can distinguish these two for the same reason. Okay. 3 here, 1, and here 2, and here we have 3. Yeah, and we didn't list the last one. Again, 3, 2, and 1. Well, and this one is very important one. In model logic, we can say that it's some kind of model where when we have possible worlds, we have relations, and we have 3 types of relations of first agent, relation with first, connection with label 2, connection with label 3, so 3 types of labels, and a special function that shows the value of this face. Well, not value, but if the face is muddy or not. So we have 3 parameters, p1, p2, and p3, and this function, well, it's not really fun. Well, it can be treated as function. So it takes a combination, or maybe part of combination. So p of this, and the result is the set or subset of possible worlds where this variable is true. Well, in our example, is black, for example, and so on for every variance here. And then there are several axioms and so on. So I think we shouldn't dive deeper right now because it's not a course of logic. Though maybe we will need it in developing our software. Then I will share with you the knowledge of this theory. There are special courses on this and so on. But for our case, for our specific case, what we have? So we have uncertainty. We have different knowledge of, and it is very important that there is no mistakes. So all children, they are not, well, there is no lie. So they say truthful information. They just don't know. So there is no liars here. And so there is no false messages because there is a special theory about fake news and so on. It's not here. Here there is a knowledge and maybe a lack of knowledge, but there is about a truth knowledge here. It's very important because there is another theory that is slightly more complicated about beliefs. So it's not about knowledge, but about beliefs. Okay, and what we have here, okay, let we have all this situation. And we ask, so it's some kind of game here. Well, yeah, and it's the beginning. So we know that this one is real. But when a child can say that he knows if his face is muddy or not, well, in this case, he should have no other alternatives. So it shouldn't be that he cannot distinguish the world. No. He has a very certain world, any of it, but only one. And when the father, he told that there is at least one muddy, then he just told that this variant is impossible. Because before that, there is no dynamics. After public announcement, another public announcement doesn't do anything, so it doesn't work. But in this case, when we have eliminated this world, there is a dynamics. And when he asks that if they know their own faces, if they're muddy or not, then what it looks like. This third, this one, if this world is real, then for the third agent, for the third children, there is no alternatives. He had two, but one alternative had been eliminated. So for this agent here, only this world is real. And then he can say that, yes, I am muddy, my face is muddy. But it's not the case, because all of them, they are told that, they spoke that they had no information. So it's going to be true. And now you can see their dynamics here. So step by step, say no, they are moving to the real world. And at the third step, when they are asked about if they know, all of them, all three agents, they have no other alternatives, because all other alternatives have been eliminated before. So they have only one alternative, and all of them say yes, this world is real. And this is some kind of magic, but it's not. So we have, but this illustration shows us how we can use such structures to work with alternatives and to work with different situations. So when we have network, like I had before here, and we had here a different coloring, so it creates for us several possible worlds for agents. Well, for us, no, because we are just scientists. We know everything for this model. But for agents, it's some kind of uncertainty, and we can find how many worlds do we need, because violet is okay for both. So the problem is here, 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 here. So we have one variable, the second variable, the third, the fourth, the fifth, and the sixth. So we will have, and we have two possible variants. If there is an age or there is no age. So 2 in the power of 6. So for this specific case, we will have 2 in the power of 6 possible worlds, and we can connect them using the information of this coloring. And then we can proceed very similar algorithm as we did here. Okay, but it's not very easy thing. So for logicians, it's some kind of intuitive one, but it's also not very easy to do. But sometimes, but for game theoretical specialists, it's not very easy, because usually they don't like such models. Well, they don't use such models because of their special complexity. You have to know logic and you have to know game theory, so it's very difficult. So there are logicians and there are game theorists, and the place where the scientist he has knowledge of both domains is very rare. So it's not very common situation. So it's not very well developed. But there are special theories for this. Okay, it's about muddy children puzzle and so on. I have described. I think that now, well, maybe the last thing I should say here is just notation. So since we came to the logic, maybe we should say how people they use notation to talk about this. So they use notation of models. So I have described. So they have words and they have relations, and they have special formulas there. So it's some kind of box P. So they say, for example, this one and this one. It can help. This notation or this explanation will help you to read articles if you need them to create your software. So the idea is that it's the name of model of our city name, just maybe Chicago, and another thing. This is the name of the possible world, like the possible world where Batman exists, or the possible world where we have a road from the point 1 to point B. And this one means that it is true that this variable, well, this formula, well, is true at this world. It's like saying, if it is true in the world X in Chicago, in all possible variants of Chicago, that in this variant of Chicago, that P is true. And if we write this, it means that it's true. If we write this, it's true that it's not P. So it's true the opposite. And model logic is using box here. Box in philosophical or game theoretical application can be denoted like a K. It's the same here, knowledge P. It means that an agent, K with index, an agent I knows that P is true. What does it mean? This box means that if there is a world here, like here, so X here, and we have a special variable here, then it is the box 1 is true for this if in all worlds that are connected with this one, with X, connected by relations of indistinguishability of the first agent of this one, in all such worlds, this variable is true. Then we can place box. It's like a mathematical term for all. For all worlds that are connected with this one, But here it's not true, because we know that here P1 is true, Mari or Mari, and here is not. So it's not true. Or we can say that it's not true that P1 is true. But at the same time, if you want to ask an agent the first agent about P2, for example, we want to ask him here like mx the same box 1 P2, then it's true. Why? Because in all variants of the world that of Chicago, where is this true, then for the agent 1, there is no problem to distinguish P2, because he can see face of the second children, so there is no problem, and it's true. So in all possible worlds, and in philosophical thing and game theoretical thing, it means that agent 1 knows that P2 is true, because he has no alternative where P2 is not true. This is the main idea. And then they have axioms and so on. By axioms, we should be not listed here. I will mention them later if we need them. Okay, and now you have, I don't know if you need it or maybe not, but for our purposes, very important to be aware of this kind of content, so of this logical uncertainties and so on. So now you know language, at least the very beginning of this language, of talking about logic, reasoning, and epistemic models. Now we can read articles about this. From my experience, it took me about several visits to Europe, in France, to Toulouse and to Amsterdam, to understand this notation. So it was not very easy for me to understand this, but you have this for free. Okay, and now we can move forward. So we have discussed logical thing, uncertainties, and we have discussed muddy children puzzle, game theoretical ones. Okay, it looks like we have discussed all we need to solve the our problem. So what we have here, so as I have explained, we have a graph here, okay, coloring, okay, game, okay, pi. So when we have, well, the basic algorithm is take graph, create a graph of graphs there according to this coloring, and then apply, well, create games, special type games, and then find equilibrium using the definition of Nash equilibrium. I would like to show you as a well, some kind of bonus for you, an interesting game that is highly connected to our case. I don't know the solution of this. I believe that maybe people already found it, but maybe not. It is very interesting since it is has an application for the game called Go. Is a Chinese thing or Japanese. It's not very easy for me to say, but usually it is associated with Chinese culture. Now there are the AlphaGo, it's a computer based on neural networks mechanisms algorithm that can play this game Go very fast, and he can win games with humans. So there is no human that can win in the game with this algorithm. But the game itself is more complicated than chess. So you know chess, obviously, and maybe you know Go if you're from Asia, or maybe you have some such experience, because it's not very popular in Russia. Maybe in the United States it's more Asian thing, but it's well known all worldwide in machine learning especially. And there is a part of this game that when players, they have to solve such kind of problems. What is the problem? So let me have several points, and we assign for every, well, it's a game of two. Well, for us it's red the same and blue. It doesn't matter this coloring, because we can assign any other one or just number. But for me, red and blue, it's okay, like fire and sky, for example. And there are 5 choices, or maybe more choices here, and choices here. And for every choice, we have 4 numbers, like alpha 1, 1, alpha 2, 1, alpha 2, 2, alpha, well, a little bit better here, for every. And then these players, they have to choose these points step by step. First red, then blue, or then again red, and then blue again, and then red and blue, and so on, until all points will be chosen. So the if blue, he choose, well, and he chooses point this one, I have numbering, and he chooses this first. So at this point hasn't been chosen by red before. So then and they have their own utility functions, like U1 and U2, U red and U blue. It's like their budget of one of them. So, and what they have, when blue comes here, he get this number, the largest. Well, usually the high number is larger than this one. So he get better, and the red, he gets the lowest. So it assumes that if blue has chosen this place first, then red will choose this point later. So it looks like shops. So when stores, when you come to this point and you open your shop, then you're the first. So you have some kind of advantage. And customers, they think that, oh, okay, we know him, he's the first who is here, so it's an advantage. So you get more. And when a red will come there, he will have a disadvantage because he has to put a new shop, and he has to prove for customers that it was coming to his shop. So he's fighting contra status quo. So it's not very easy sometimes. So he gets this one. Well, why it is so too? Yeah, because it is low. Yeah, in the first one. And then red has to choose. He can choose this one, 3, for example, and then blue here and red here. And then red choose 3, and he had the highest variant 3, and then beta has the lowest 3, and so on. And then we plot, we summarize all this, and we get some result for this. And this is the profit in this game of every agent. There are many special cases, but this is a general one. It looks like we extensive form of it's very similar to extensive form of a Colonel Blotto game. It's the game when you have 2 objects and you have efforts or budgets of 1 player and budget of 2nd player, and you have to split how much efforts you should use on this object and on this object, like marketing. So you have a marketing budget, you have marketing budget here or marketing budget here for this target group of customers. And the winner is that seller of this agent who spent more budget, marketing budget on this object. So the customers, they will all go to this seller. And the problem is how to find an equilibrium. So if I know budgets, and for example, they're the same, and we have many objects, maybe of different values, how should we split our budget into several parts? And there is a solution. So there is very simple strategy, mixed equilibrium and mixed strategy and Nash equilibrium, but it's not in our focus right now. But it's very similar for this. Okay, this is the game. Okay, but what is the solution? So if I were the red player or blue player, and I was asked to make a move, to make a choice, what point should I take first, and then what point should I take the second? Well, I don't know right now. I believe that there should be an algorithm how we can define this, but right now I cannot say. I believe that branch and bound algorithm or maybe some others can help to find, but I cannot see any very obvious, intuitive or greedy algorithm that can be applied here. It looks like, for example, greedy algorithm means that you should take on the values, the largest one. But in this case, it could be, it might be that another thing here, for example, you have this value is very large, but it's this point is not interesting for my opponent at all, or even he has -3, -6, so he has only costs here. He don't has real benefits here. And in this case, even if beta is large here, maybe I don't need to choose it. Maybe I should choose another variant, and then I will go back to this variant because I know that red will never choose it. But another thing where better, for example, third. Here is large, not as large as this one, but large, but it's very interesting for red, because here for red it's like a 10 and 20 is much larger than this one, and for red it's very interesting point. And then maybe it's a good strategy for blue to choose this point, then red choose another point, maybe not absolutely not interesting for blue, and then blue choose the most interesting for him variant. And maybe it's the best strategy. It looks like the best strategy in this example. So the greedy algorithm is wrong, generally wrong. But what algorithm will work? And I don't know really. Well, I can try, and if you know how to find this algorithm, you can include it into your, I don't know, maybe not homework, in your project, maybe, if you know the solution. Okay, we have only 10 minutes to discuss, so I have explained this one as a bonus. And well, hmm, really I'm able to describe why it is so connected with Go, with Baduk or Go, this game, but in this case I should tell rules of this game, and it will take time. That it takes time, and I don't think that I should do this, because you can read it in internet. Okay, so logic here, so game theory. If you have any question, it's a good time to ask, because we have only 9 minutes before we stop today until the next lecture. So you can ask me. If not, okay, sorry, wait a minute. Okay, so we will continue. So we have several minutes. If you have questions, you can ask me. I will try to answer right now. If not, I will continue with our lecture and try to explain some other terms. So maybe, well, yeah.
Basically, I wanted to know if you could recommend books.
Okay, yeah, I will send you links to books that you can read, and there are a lot of information about these games, especially about logic. But some information is not available. It's available only in articles in a very specialized literature. But I think I can share with you, and you just look through, and maybe you will understand the basic idea of this, or maybe all the content of this article. It's okay. Thank you for this question. I will try to find the list of literature references that will be helpful for you. Okay, thank you. That's okay?
Okay, thank you so much.
Okay. And now I would like just in these 5 minutes recall the basic ideas of our lecture today. So we have discussed the hoteling game. The hoteling game is sometimes about ice creams on the beach, as I have told. So I will show you the picture here. So the hoteling is a professor. he already dead, but he's very famous, and he has a lot of hoteling law, hoteling rule, and other hoteling objects in mathematics. He was very famous. So, and he had invented and described. He investigated the properties of a game when we have a beach, and we have a beach here. So we have a territory, A territory and B territory here, and we have two sellers here there, and they have to find their position there. So we have a position for A, and we have a position for B. In all my description, you can think about it as like a red one and a blue one territory, and we have a universal distribution of customers, and customers they just on the beach, they have a rest, swim, and they have money to buy ice cream. And but the algorithm of them is just to choose that man who is closer to his point than another. It's very intuitive. I don't want to walk more if I can buy the same ice cream right here. So it's okay. It's very interesting thing. But there is a game because it can be not symmetric. For example, if he make first move and he plays his position in the center of this beach, then the second he has to choose left or right, but in any case he will get only smaller part of this territory, because all other half of this territory will belong to his opponent, and also his opponent will have a part of his half. So it's very profitable to make a first move here, and the second player lose. But if they play normal form game, or they have several points, for example, this seller blue one, he has not only 1 point, and maybe he has employers. So he has 3 employers, and there is a place for the first employer, the second, and the third. So there is a game of several shops. So there is an idea, and we can find equilibrium here, and so on. The hoteling game is very famous, but we decided to apply it and connect with our logistics problems, because in our logistics problem we had like traveling salesman problem, or we were looking for a position for our shops and for bank offices, as I have described before, and we did it on the graph. There is no graph indeed. So there is, where is graph? But we can apply it, and we can see that we can do it easily. So when we have a graph, we can place, and we can we can place customers. We can assign customers to every point. For example, it can be cities or can be blocks in the big city. For example, if we are talking about Moscow, it can be Kremlin, or it's the central part of Moscow. It can be not central, and this road is just the traffic. How much time I need to move from this point to another one, and so on. And we want to place our shop, supermarket, IKEA, for example, or Auchan, or any other, and we have to choose the place, and we want to compete with others, with other guys who have, for example, Auchan wants to compete. I don't know who. Well, with some other supermarket here, and then we have to choose, and we can, for very large graph, we can allow only several points to place shops. It makes our big graph of city not very scary, because in our algorithm, complexity depends on the number of nodes. But if we allow only several points for our shops, then we reduce complexity, and then we can solve it as it were very small graphs. We just have to find the way how to compute number of customers. So we have to find. We can define this like arrows. So if a shop is here, so then where should this customer go? The here or maybe to another one? And then I have introduced several modifications for this: multi-agent, multi-shops, external, extensive form, normal form game, and so on. We have discussed, oh, sorry, some ideas of this, how we can do this. And then we have discussed logic and strategies and so on. And I have explained the basic idea of homework here. I will create a special, well, make a file and I will describe it formally. The deadline is by the end of the fourth model, but I'd like to have some feedback by the end of the third model. So, but it's not for 1 week homework. It's homework for large period. But maybe I will ask you to make a smaller part of this homework, maybe in 2 weeks or 3 weeks, just to make sure that you are in the process of making this software. And it will be not a surprise for me to find that maybe you don't understand something and you didn't create the software at all. So it will be very difficult to make it at the last time. Okay, so I have 1 minute more. Thank you for coming today. I'm very happy that you came because at the beginning of the lecture, there were no students and I was some kind of worry about this, but now you're here, so it's great. I hope I was useful now, and see you next week. We will continue with this discussion, and maybe we will come back to this branch and bound algorithm and other theoretical aspects. Thank you. This video I will upload to our chat, Telegram chat at YouTube. So it will be available for you and other students. Thank you.